There is a galaxy so vast that light itself would need millions of years just to travel from one edge to the other. Not thousands, not even hundreds of thousands. Millions of years. For light to cross a single galaxy, that number alone should already feel uncomfortable. At first, it sounds like the end of the story. The biggest galaxy ever found. Case closed. But here's the problem. The biggest galaxy isn't just one thing. In the universe, big doesn't mean what we think it means. One galaxy is enormous because it holds more stars than we can realistically count. Its size comes from mass, from gravity, from matter slowly piling up over billions of years. Another galaxy is enormous for a completely different reason. Not because of what it contains, but because of what it does. It launches energy in opposite directions, far beyond any boundary we once believed possible. So far that its true size can't be seen with human eyes at all. Both of these objects are real. Both are confirmed by modern astronomy. And one of them looks almost ordinary, until you learn how to see it properly. This isn't a video about ranking galaxies or arguing which one is number one. It's about discovering why the universe keeps outgrowing our intuition, no matter how advanced our measurements become. And while these cosmic giants continue their quiet work out there in the dark, nothing is required of you right now. Tonight, you get to rest. Let's start with the galaxy that's big in the most literal way possible. Big because of what it actually contains. Its name is IC 1101. IC 1101 sits at the very center of the massive Abell 2029 cluster, more than 1 billion light-years away from Earth. Even at that distance, astronomers noticed something unusual. Not because it was bright or dramatic, but because its scale refused to make sense. The estimated diameter of IC 1101 stretches between 4 and 6 million light-years. To understand what that means, we need a familiar reference. The Milky Way, our home galaxy, spans about 100,000 light-years across. That already feels enormous. IC 1101 is dozens of times larger. And the comparison becomes even more unsettling when you imagine this. If IC 1101 replaced the Milky Way, its outer edges would extend far beyond our local cosmic neighborhood. It wouldn't just replace our galaxy. It would swallow the entire local group, enveloping the Milky Way, Andromeda, and dozens of smaller galaxies inside a single, continuous structure. Yet visually, IC 1101 doesn't look like a typical giant. At a glance, it can seem almost plain. That's because IC 1101 is an elliptical galaxy. Smooth, rounded, and quiet. But that quiet appearance hides something far more extreme. IC 1101 is large because it has been accumulating matter for an incredibly long time. Sitting at the gravitational center of an entire galaxy cluster, it has spent billions of years pulling material inward. Smaller galaxies drifted too close. Their stars were stripped away. Their mass was absorbed. Over time, IC 1101 grew heavier, wider, and denser. Not through explosions, but through patience. This is what big looks like when measured in actual matter. IC 1101 doesn't announce itself. It doesn't flare or pulse. It simply exists, immense, ancient, and heavy, acting as a quiet gravitational anchor that has been shaping its surroundings for longer than complex life has existed on Earth. This is the first giant, and its size only becomes truly shocking when you realize how many stars a galaxy like this can actually hold. IC 1101 contains an estimated 100 trillion stars. To put that into perspective, our home galaxy, the Milky Way, holds about 400 billion stars, If you counted one star every second, it would take 12,000 years to count the Milky Way alone. But for IC 1101, it would take 3 million years. That span of time is longer than the entire history of human civilization. This is where the human brain begins to surrender. We were never designed to intuitively understand numbers like these, but we can measure them. And what's even more remarkable is that each of those stars may host planets of its own. The universe does not shrink itself to fit human understanding. Instead, it forces us to expand the boundaries of our thinking. And to truly grasp how extreme IC 1101 really is, we need to place it next to something familiar: the galaxy we call home. Our home galaxy, the Milky Way, is a barred spiral, a flat disk with sweeping arms and a bright central bar. From one side to the other, it measures about 100,000 light-years across. That number already sounds enormous. Light itself needs 100,000 years just to cross it. Inside the Milky Way are roughly 200 to 400 billion stars, each one a sun in its own right, each one part of a structure so large that we can't see it all from within. And yet, even with numbers like these, the Milky Way is not considered exceptional. Our solar system sits in the Orion Arm, far from the galactic center. We don't live in a special region. We don't orbit anything unusual. From a cosmic perspective, our location is quiet, stable, and remarkably ordinary. When astronomers compare the Milky Way to the broader population of galaxies, a clear picture emerges. It's not small, but it's not large either. It's average. Now place that average galaxy next to IC 1101. The Milky Way's 100,000 light-years suddenly shrink in meaning. IC 1101 stretches millions of light-years across. Where our galaxy holds hundreds of billions of stars, IC 1101 holds numbers that push into the trillions. What once felt impossibly vast becomes a reference point instead. This is the quiet shock of astronomy. The structure we call home, the galaxy that defines our night sky, our myths, and our sense of place, turns out to be a mid-sized example in a universe filled with far larger constructions. That realization doesn't make the Milky Way less meaningful. It makes the universe more honest. Home feels special because it's familiar, not because it's the biggest. Let's return to IC 1101. Size alone doesn't explain its most striking feature. It's quiet. IC 1101 is an elliptical galaxy. Unlike spiral galaxies, it has no sweeping arms, no bright lanes of dust, and no glowing pockets where new stars are being born. Its shape is smooth and rounded, almost softened by time. The reason is simple and ancient. Most of the stars inside IC 1101 are very old, formed billions of years ago, when the universe itself was younger and richer in cold gas. Over time, that gas was either used up to make stars or heated and pushed outward, no longer able to collapse and form anything new. As a result, star formation slowed, and then nearly stopped. What remains is a galaxy filled with aging stars. They shine steadily, not brightly. Their combined light gives IC 1101 a warm, yellow-red glow, the color of stellar populations that have long since passed their energetic youth. Its environment makes this quiet permanent. IC 1101 sits inside a hot, gaseous cluster atmosphere. This surrounding gas stays too warm to cool and fall back into the galaxy. Without fresh, cold material, there is nothing left to spark new generations of stars. So IC 1101 doesn't flicker or pulse. It simply endures. A useful way to imagine it is not as a machine, but as a city. A very old city. The streets are wide. The buildings are massive. Everything feels established and immovable. Life continues. but slowly. The energy of growth has long since passed, replaced by stability and weight. This is the cost of becoming so large. Galaxies that grow quickly and violently burn bright, but briefly. Galaxies that grow slowly and steadily, like IC 1101, trade brilliance for longevity. Here, greatness doesn't announce itself. It settles in. This is why one of the largest galaxies ever discovered can appear almost calm. Its most dramatic moments happened long ago, written into the ages of its stars rather than into bursts of light. And that calm is not emptiness, it's maturity. Because at the center of this quiet giant lies something far darker and far more extreme. At the heart of IC 1101, there is something even more extreme than its size: a supermassive black hole. Astronomers estimate that this central black hole weighs between 50 and 70 billion times the mass of our Sun. Numbers like that are difficult to anchor, so let's return to something familiar. At the center of the Milky Way sits Sagittarius A, a black hole with a mass of about 4 million suns. It dominates our galaxy's core. It shapes the orbits of stars near it. And yet, compared to the black hole inside IC 1101, it is almost insignificant. The difference is not a few times larger. It's tens of thousands of times larger. And still, this enormous black hole is not a raging monster. It isn't constantly feeding. It isn't blasting radiation into space. It may, in fact, be relatively quiet right now. That's an important distinction. Black holes don't need to be active to be powerful. Even in silence, their gravity shapes everything around them. This one anchors the entire core of IC 1101, guiding the motion of stars, influencing the flow of gas, and stabilizing a galaxy that spans millions of light years. A useful way to imagine it is not as a creature, but as a center of balance. Every orbit in the galaxy ultimately responds to this mass. Every large-scale motion traces back to its gravitational pull. The black hole doesn't need to move. Everything else moves because of it. This is why black hole mass matters so much to astronomers. As Avi Loeb once put it, the mass of a black hole tells the story of a galaxy's entire growth history. A black hole this large didn't form overnight. It grew through mergers, through accretion, through repeated cosmic encounters across billions of years. Each event added mass. Each collision left an imprint. What we're seeing at the center of IC 1101 is not just a black hole. It's a record, a fossil of everything the galaxy has absorbed and survived. And yet, for all its mass, it remains invisible. There's no surface to see, no outline to trace, only its influence, written into the motion of stars and the structure of the galaxy itself. This is the paradox of extreme gravity. The largest forces often announce themselves in the quietest ways. Here, power doesn't roar, it holds. And the evidence of that long, violent history is written directly into the core of the galaxy itself. There is one more feature of IC 1101 that astronomers find impossible to ignore: its core. At the very center of this galaxy lies a region so large that it defies expectations. The core of IC 1101 spans tens of thousands of light years across, far larger than the cores found in most galaxies. In a typical galaxy, the central core is relatively compact, dense, bright, and tightly bound. But in IC 1101, the opposite is true. The core is broad, diffuse, and strangely empty of stars. This isn't a mistake in measurement, it's a clue. Astronomers believe this oversized core is the result of repeated black hole mergers over the galaxy's long history. Here's how that process works. When two massive galaxies collide, their central black holes don't merge right away. Instead, they begin to orbit each other. locked in a slow gravitational dance. As they spiral closer, their combined gravity becomes extremely disruptive. Stars that wander too near are flung outward. Some are ejected into wider orbits. Others are thrown completely out of the core region. Over time, this process scours the center of the galaxy. Each merger clears out a little more space. Each encounter pushes more stars away from the middle. The result is a core that grows larger not because material is added, but because material is removed. This is why IC 1101's core appears hollow compared to its immense size. It isn't empty by accident. It has been carved by gravity, shaped by events that unfolded over billions of years. And those events didn't happen once. They happened again and again. Every major collision left a mark. Every merger rewrote the structure of the galaxy's center. What we see today is the cumulative record of those ancient encounters, preserved not in explosions or light, but in the absence of stars where they once should have been. In that sense, IC 1101 is more than a galaxy. It's a memory. Its core holds the scars of a violent past, a history of absorption, collision, and survival that unfolded long before our planet existed. The galaxy doesn't announce that history. It simply carries it forward, embedded in its structure. This is the price of extreme growth. To become this large, IC 1101 had to endure repeated upheaval. Its calm exterior hides a center that was shaped by some of the most energetic events the universe can produce. The core is wide, not because the galaxy lacked material, but because it experienced too much of it. And with that realization, the story of IC 1101 reaches its natural conclusion. Because stars and mass are not the only way the universe defines something as big. Before we court, after everything we've seen, one thing is clear. IC 1101 is enormous in every traditional sense. It's large in stars, large in mass, large in gravity, even large in the size of its core and its central black hole. By most standards, that should settle the question. But astronomy rarely works that way, because once we start asking what biggest really means, the answer depends entirely on how we choose to measure it. Is a galaxy big because of how many stars it contains, because of how much mass it holds, because of how far its faint halo extends into space? Or is it big because of something else entirely? Astronomers don't rely on a single definition of size. Different measurements reveal different truths. Each one tells a separate chapter of the same story. And that's where things begin to shift. Some galaxies don't stand out because they are packed with stars. They don't dominate because of mass alone. Instead, they create structures that stretch far beyond their visible bodies. Structures that extend into the surrounding space on scales that rival and sometimes exceed anything built from stars. Here's the key idea. The largest structure connected to a galaxy isn't always made of stars. In fact, some of the most extreme examples of big in the universe are almost completely invisible in ordinary light. They don't glow, they don't shine, they don't announce themselves in the night sky. If you looked at them with your eyes, you would see almost nothing at all. And yet, these structures can span millions of light years. This is where the story turns. Because to see this different kind of size, we have to let go of the idea that brightness equals importance. In the universe, big does not always mean bright. And what matters most isn't always what we can see. To uncover this next kind of giant, astronomers had to stop looking with ordinary telescopes. They had to observe the universe in a completely different way, using a form of light that reveals energy instead of stars. And when they did, something extraordinary emerged. And in radio light, the universe reveals something extraordinary. In 2022, astronomers announced the discovery of something that quietly rewrote the meaning of size. They named it Alcyoneus. What makes this discovery remarkable is not just what it is, but how it was found. Alcyoneus wasn't revealed by a brand new telescope or a sudden flash in the sky. It emerged from a careful reanalysis of existing data collected by LOFAR, a vast network of radio antennas spread across Europe. Nothing new was added. Nothing dramatic happened. Scientists simply learned how to look differently. At first glance, the galaxy at the center of Alcyoneus appears unremarkable. Looks like an ordinary radio galaxy, modest in stars, unassuming in visible light, easily overlooked among billions of others. But when viewed in radio wavelengths, something extraordinary appears. From this quiet central galaxy, two colossal streams of energy extend in opposite directions. Vast radio lobes powered by jets from the galaxy's central black hole. These structures stretch outward far beyond anything we're used to seeing. When measured from end to end, Alcyoneus spans around 16 million light-years. Let that settle for a moment. 16 million light-years. For comparison, the Milky Way is about 100,000 light-years across. That means Alcyoneus extends roughly 160 times wider than our entire home galaxy. And this isn't a cluster. It isn't a filament of many galaxies. It's a single structure tied to one central galaxy. This makes Alcyoneus the largest structure ever associated with an individual galaxy. What's most unsettling is how easy it was to miss. In visible light, Alcyoneus is almost invisible. Its radio lobes don't glow. They don't reflect light. They don't announce themselves to human eyes. If you were to point an optical telescope at the region, you would see very little that suggests something this vast exists. That's why Alcyoneus feels like a kind of cosmic ghost. It has always been there, stretching across millions of light-years, but only reveals itself when observed in the right way. The structure itself is shaped by energy, not stars. The radio lobes are filled with high-energy particles and magnetic fields, flowing outward from the galaxy's core at near relativistic speeds. Over immense spans of time, these jets inflate enormous bubbles of radio emission, carving their presence into the surrounding cosmic medium. Unlike IC 1101, which grew large by accumulating matter, Alcyoneus grew large by projecting energy. This is a completely different expression of big. Its size is not measured in how much it contains, but in how far its influence reaches. The central galaxy didn't need to be extraordinary in appearance. It didn't need billions more stars. What mattered was the power and persistence of its central engine, sustained long enough to push energy across intergalactic space on a scale never seen before. This discovery forced astronomers to confront an uncomfortable truth. If something this enormous could exist unnoticed for so long, how many other structures might still be hidden? Not because they are rare, but because we haven't yet learned how to see them. Alcyoneus doesn't challenge our measurements. It challenges our assumptions. It reminds us that the universe is not limited by what our eyes can detect. Size, in this context, becomes a property of reach, not brightness, of impact, not appearance. This is what big looks like when measured in energy rather than matter. And it raises a question that lingers uncomfortably. If Alcyoneus is the largest structure tied to a single galaxy ever found, why did it take us so long to notice something this enormous at all? That question leads us directly to what comes next. By now, one question naturally follows. If Alcyoneus is truly this vast, how did it remain unnoticed for so long? The simplest answer is also the most unsettling. It was always there. For decades, astronomers mapped the sky using surveys designed for objects that were bright, compact, and well contained within a single frame. Those tools worked beautifully for stars, galaxies, and even galaxy clusters. But Alcyoneus didn't fit the picture, literally. Its radio structure stretches across millions of light years, far larger than the typical field of view used in earlier surveys. When telescopes looked at parts of it, they saw fragments. The edges were cut off. The full shape never appeared at once. It's like standing too close to a massive mural. You see colors, you see texture, but you never see the image. There was another problem. Older radio surveys were not sensitive enough to detect very faint, low-frequency emission spread thinly across enormous distances. Alcyoneus doesn't shine brightly. Its radio lobes are diffuse, subtle, and easy to confuse with background noise. So the data didn't scream for attention. It whispered. That's where LOFAR changed everything. LOFAR was designed specifically to listen to the universe at low radio frequencies, where older, more extended structures reveal themselves. Its wide coverage and high sensitivity made it possible to connect what once looked like unrelated patches into a single, coherent structure. Nothing new had to form. No explosion occurred, no sudden appearance. Astronomers simply assembled the pieces. When they did, the full scale of Alcyoneus became impossible to ignore. This is an important distinction. Alcyoneus didn't suddenly become large, and it wasn't hiding. It existed in plain sight, just beyond the limits of how we were used to looking. That's why its discovery is not a fluke or a mistake. It's the natural result of better tools and broader perspective. When observation methods improve, the universe doesn't change. Our understanding does. This pattern has repeated throughout the history of astronomy. Every time we extend our senses into a new range of light, we uncover structures that were previously invisible, not because they were rare, but because they were outside our frame. Alcyoneus is a reminder of that truth. Sometimes the universe doesn't conceal its giants. It simply makes them too large to fit inside the picture we've drawn. And now that we can finally see the whole thing, a deeper question emerges. How does a galaxy create structures this vast in the first place? That question takes us to the engine behind it all. At the center of Alcyoneus lies a familiar engine, a supermassive black hole. But what makes Alcyoneus extraordinary is not the black hole itself. It's what the black hole does with energy. When gas and dust drift toward a black hole, they don't fall straight in. Instead, they form a spinning accretion disk, heating up as friction and gravity squeeze the material tighter and tighter. Temperatures rise, particles accelerate, and powerful magnetic fields begin to twist and align. Those magnetic fields act like rails. They gather energy from the disk and the black hole's rotation, then focus it into two narrow channels, one shooting outward above the disk, the other below it. These are jets. They aren't beams of light. They're streams of hot plasma, electrons, and charged particles, launched at extraordinary speeds. In extreme cases like Alcyoneus, those jets can reach up to 98% the speed of light. At those velocities, even a small amount of matter carries immense energy. What makes this possible is the environment the jets move through. Intergalactic space is incredibly thin. far emptier than anything we can reproduce on Earth. With almost nothing in their way, the jets travel outward for millions of years, losing energy only slowly. As they move, they inflate vast regions of radio-emitting plasma. These regions don't glow in visible light, but they shine clearly at radio wavelengths, tracing the path of energy far beyond the galaxy itself. This is how Alcyoneus becomes so large. Not by collecting stars, not by gathering mass, but by continuously projecting energy into space. As long as the central engine remains active, even at a low level, the jets keep feeding the structure. Over time, the radio lobes expand, stretch, and grow until they span distances measured in millions of light years. In this sense, the galaxy isn't building an object. It's drawing a shape made of motion, magnetism, and time. This is why size, in the case of Alcyoneus, cannot be understood by counting stars or weighing matter. Its scale comes from flow, not from substance, from energy sustained long enough to leave a permanent imprint on the surrounding universe. Here, big is not something you can hold or see directly. It's something that moves. And this is only part of the story. Because when those jets interact with magnetic fields spread across intergalactic space, the universe reveals just how far energy can really travel. To understand why Alcyoneus appears so vast in radio light, we need to follow the energy it releases, step by step. It begins at the center, where the black hole launches powerful jets. These jets carry electrons moving at nearly the speed of light, streaming outward into intergalactic space. Electrons are electrically charged, and when charged particles move through magnetic fields, something important happens. They don't travel in straight lines. The magnetic fields gently bend their paths, forcing the electrons into curved motion. And whenever charged particles are accelerated or curved in this way, they release energy in the form of electromagnetic radiation. This process is called synchrotron radiation. It's not an explosion. It's not a flash. It's a steady, continuous glow, strongest at radio wavelengths. That detail matters. Human eyes are only sensitive to a very narrow slice of the electromagnetic spectrum, visible light. But the largest structures created by Alcyoneus emit almost entirely outside that range. They don't shine in colors we can see. They radiate quietly at wavelengths far longer than light. This is why Alcyoneus looks ordinary in optical images. The biggest parts of it are simply invisible to human eyes. When astronomers observe Alcyoneus in radio light, a very different picture emerges. On either side of the central galaxy, enormous clouds of energized plasma appear. Vast lobes filled with electrons spiraling through magnetic fields. These lobes aren't static objects. They grow slowly. Over millions of years, the jets continue feeding them. Energy spreads outward, gradually inflating the structure, pushing farther into the thin intergalactic medium. With almost nothing to stop them, the radio-emitting regions expand to truly staggering scales. This is how size emerges, not from stars, not from solid matter, but from motion sustained over time. As long as energy keeps flowing, the structure keeps growing. The result is a system where the most extended regions are also the faintest, wide, diffuse, and easy to miss, unless you're looking in exactly the right way. In Alcyoneus, energy travels farther than matter ever could. Stars remain bound by gravity. Gas cools and settles, but energized particles, guided by magnetic fields, can cross distances that would be impossible for solid structures to maintain. That's the key difference. IC 1101 became large by accumulating mass. Alcyoneus became large by never letting its energy stop moving. This is why its true size doesn't reveal itself in photographs or visible light surveys. It only appears when we listen to the universe in radio frequencies, where motion, not brightness, defines the scale. In the universe, size doesn't always come from what something contains. Sometimes, it comes from how far energy is allowed to travel. And now that we've seen how synchrotron radiation turns motion into structure, we're ready to step back and look at the bigger picture. Because we've now encountered two very different kinds of giants. And they couldn't be more different at all. By now, we've met two giants of the universe. And they could not be more different. On one side stands IC 1101. It is enormous because of what it contains. An immense number of stars, an extraordinary amount of mass, a vast, hollowed core, and one of the most massive black holes ever measured. IC 1101 grew large by accumulation. Over billions of years, gravity pulled matter inward. Galaxies merged, stars were stripped and absorbed. Everything added weight, everything stayed. Its size is heavy, anchored, still. Now compare that to Alcyoneus. Alcyoneus is not defined by how much it holds, but by how far it reaches. Its central galaxy is relatively ordinary. What makes it extraordinary are the jets. Streams of energy launched from its core and carried across intergalactic space. Those jets inflate colossal radiolobes, not made of stars, not made of solid matter, made of motion, magnetism, and time. Alcyoneus became large by extension. Nothing settled, nothing stayed still. Energy kept moving, and the structure kept growing. This is the critical distinction. IC 1101 is large because matter piled up. Alcyoneus is large because energy never stopped flowing. One represents size built from mass. The other represents size created by motion. And this is why asking which one is bigger misses the point. They aren't competing for the same title. They aren't even playing the same game. Astronomy doesn't offer a single definition of size because the universe doesn't express scale in a single way. Sometimes, size is about gravity and weight. Other times, it's about reach and influence. Once you let go of the idea that big must mean one thing, something interesting happens. The universe starts to make more sense. Its extremes stop contradicting each other. Instead, they reveal different strategies, different outcomes, shaped by the same underlying laws. IC 1101 shows us what happens when matter dominates. Alcyoneus shows us what happens when energy is allowed to run free. Two giants, two definitions of big. And together, they expose something far more important than any record. They reveal the limits of how we usually think about scale. Because these giants don't just challenge our measurements. They challenge our understanding. And that's where the story leads next. Modern cosmology works remarkably well. With a small set of equations and assumptions, scientists can explain how galaxies form, how they grow, and how structure emerges across the universe. These models accurately reproduce most of what we observe. Spiral galaxies, elliptical galaxies, clusters, and the large-scale web of matter stretching across space. For the majority of the universe, the math behaves. But every so often, something appears that sits uncomfortably at the edge of those models. Objects like IC 1101 and Alcyoneus fall into that category. They are not typical galaxies. They are extreme. In large-scale computer simulations of the universe, systems this massive or this extended are expected to be extraordinarily rare. Some simulations produce only a handful. Others produce none at all. And when they do appear, they often take longer to form than the universe has existed. That creates a quiet tension. The universe is about 13.8 billion years old. Within that time, galaxies must grow, merge, and evolve. For IC 1101 to accumulate so much mass, and for Alcyoneus to project energy across millions of light years, everything had to happen efficiently, almost too efficiently. So astronomers ask careful questions. Did these systems form in unusually dense environments, where growth was accelerated? Did early conditions in the universe favor rapid expansion in rare locations? Or are our models missing subtle ingredients, processes that matter only at the most extreme scales? Importantly, none of this means the science is broken. When scientists say, "We don't fully understand this yet," they are not admitting failure. They are identifying the exact places where knowledge can grow. Science has always advanced this way, not by what fits neatly into our expectations, but by what refuses to. Extreme objects force theories to stretch. They test assumptions. They reveal where approximations begin to fail. In doing so, they quietly improve our understanding of everything else. What once looked like an anomaly often becomes a guidepost. That's why galaxies like IC 1101 and structures like Alcyoneus are so valuable. They don't undermine cosmology. They refine it. They show us where our maps are still incomplete, where the universe is more creative than our equations allow. And there's something deeply human about that moment. Standing at the edge of what we know doesn't diminish us. It places us exactly where discovery begins. We don't learn the most by confirming what we already believe. We learn by encountering what shouldn't exist, and then exists anyway. Those moments remind us that the universe is not obligated to be simple. It is only obligated to be real. And beneath all of this, the stars, the jets, the unanswered questions, lies something even more fundamental, something we cannot see at all. When astronomers measure how fast stars move inside galaxies, something strange appears. They move too fast. Based on the amount of visible matter, stars, gas, and dust, many galaxies should be flying apart. Their outer stars should drift away into space. And yet, they remain bound, stable, and intact. Something unseen must be holding them together. That unseen component is known as dark matter. Dark matter does not emit light. It does not reflect light. It does not absorb light. In fact, it doesn't interact with ordinary matter at all, except through gravity. And gravity is enough. Astronomers infer the presence of dark matter by its effects. Galaxies rotate faster than visible mass allows. Galaxy clusters remain bound when they shouldn't. Gravitational lensing bends light more strongly than stars alone can explain. The conclusion is unavoidable. Most of the mass in the universe is invisible. Every large galaxy is embedded in a vast dark matter halo, an extended spherical cloud of mass that stretches far beyond the stars we can see. This halo provides the gravitational scaffolding that allows galaxies to form, grow, and survive. For giants like IC 1101, dark matter is essential. Its enormous size and mass would not remain stable without a massive dark halo anchoring the galaxy and its surroundings. And for structures like Alcyoneus, dark matter shapes the environment the jets expand into. The thin intergalactic medium, held in place by gravity, determines how far energy can travel and how large radiolobes can grow. In both cases, the visible universe is only the surface layer. The deeper structure, the one doing most of the work, remains hidden. This changes how we think about big. A galaxy is not defined only by what we can see. Its true scale includes everything exerting gravitational influence, even if it never shines. In that sense, size is not about brightness. It's about control. Dark matter controls how galaxies rotate. It controls how clusters assemble. It controls how cosmic structures endure over billions of years. What's most remarkable is how quietly it does this. There are no flashes, no signals, no images to admire. And yet, without dark matter, galaxies like IC 1101 could not exist as they do. Without it, structures like Alcyoneus would have no stable stage on which to unfold. This is one of the universe's deepest lessons. What you can see is rarely the whole story, and what you cannot see often matters the most. Light gives us beauty, but gravity reveals truth, and even dark matter is not the final layer beneath these giants. So far, we've talked about forces that hold the universe together. Dark matter provides the invisible gravity that binds galaxies and clusters. It keeps stars in orbit. It gives structure a stable framework. But there is another influence at work, one that does the opposite. If gravity is always pulling inward, a natural question follows. Why is the universe still expanding? And why is that expansion getting faster? The answer is something we call dark energy. In 1998, astronomers studying distant type Ia supernovae made a surprising discovery. These exploding stars act like cosmic mile markers. By comparing how bright they appear with how fast they are moving away, scientists realize something unexpected. The expansion of the universe is accelerating, not slowing down, not balancing out, speeding up. Dark energy is the name we give to whatever is causing this acceleration. Unlike gravity, it doesn't pull matter together. It works on space itself, gently stretching it, causing distant regions of the universe to drift farther apart over time. What makes dark energy especially strange is its dominance. It accounts for roughly 68% of the total energy content of the universe. That means most of the cosmos is driven by something we cannot see, cannot isolate, and do not yet fully understand. And its influence grows with time. On small scales, inside galaxies and clusters, gravity still wins. Stars remain bound. Systems like IC 1101 remain intact. Structures like Alcyoneus can still form and persist. But on the largest scales, dark energy slowly takes over. Over immense spans of time, galaxy clusters drift away from one another. The space between them stretches faster than gravity can bridge. Eventually, each cluster becomes isolated, an island universe surrounded by ever-expanding emptiness. This isn't a catastrophe, and it's not an explosion. It's not something that happens suddenly. It's simply the universe continuing its long, quiet expansion. Even the largest structures we've discussed, giants built from mass, energy, and time, are temporary arrangements. They exist within a universe that is always changing, always moving toward a future where distance becomes the defining feature. There's a certain calm in that idea. The dark energy doesn't erase galaxies. It doesn't tear stars apart. It just ensures that nothing stays close forever. And perhaps the most humbling part is this. The force that shapes the ultimate fate of the universe is also the one we understand the least. Most of reality is driven by something unseen. Most of the future is shaped by something unnamed. Yet, even so, the universe remains coherent, predictable, measurable. It continues to follow rules, even when we don't yet know what all of them are. And because light itself takes time to travel across space, there's one final twist to this story. We never see these giants as they are now. There is a quiet rule that governs all of astronomy. Light takes time to travel. It moves fast, faster than anything else in the universe. But it is not instant. And because of that simple fact, every time we look into space, we are also looking into the past. The farther away an object is, the older the light we receive from it becomes. This changes everything. When we observe IC 1101, we are not seeing it as it exists today. We are seeing it as it was more than 1 billion years ago, long before modern life appeared on Earth. The light reaching our telescopes left that galaxy when our planet was still changing rapidly, when continents were shifting and early life was reshaping the atmosphere. The same is true for Alcyoneus. Its enormous radio structure appears to us as it existed in a distant past, when Earth itself was far younger. Whatever those jets are doing now, whether they have faded, shifted, or grown even larger, we cannot know yet. We are always delayed observers. This is why astronomy is often described as a form of cosmic archaeology. Archaeologists reconstruct ancient civilizations from fragments of stone and bone. Astronomers do something similar, but with photons. Each particle of light is a record, a message sent across time, carrying information about conditions that no longer exist. Every telescope is, in a sense, a time machine. Not because it lets us travel through time, but because it shows us layers of history stacked across the sky. Different distances reveal different eras. Different wavelengths reveal different chapters of the same story. What we never see is the universe as it is right now. There is no cosmic present moment available to us. The universe's current state is always just beyond reach, separated from us by the finite speed of light. And yet, this limitation is also a gift. By studying these delayed images, these frozen moments, astronomers can piece together how galaxies grow, how energy spreads, and how structure evolves over billions of years. We learn not from snapshots of the present, but from sequences of the past. Our understanding of the universe is always a reconstruction, a careful assembly of echoes. And somehow, from all of this, from ancient light, invisible forces, and structures too large to fully imagine, the universe produced something capable of reflecting on it. Something capable of asking these questions at all. After everything we've explored, the vastness of IC 1101, the reach of Alcyoneus, the invisible forces shaping them, it's easy to feel very small. But here's something worth pausing on. Both of those giants, different as they are, formed from the same basic ingredients that exist inside you. The carbon in your cells, the oxygen in your blood, the iron in your bones. All of it was forged long ago inside stars. Stars that lived, burned, and died before Earth ever existed. Those elements were scattered into space, recycled into new generations of stars and planets, and eventually assembled into a world capable of asking questions, into minds capable of wondering. That's the quiet connection. You are not separate from this story. You are part of it. There's a line often attributed to Carl Sagan that captures this perfectly. We are star stuff thinking about star stuff. It's not meant to elevate us above the universe. And it's not meant to diminish us either. It simply places us where we belong. We are small compared to galaxies that span millions of light years. We are brief compared to cosmic timescales measured in billions of years. But size and duration are not the only measures that matter. Despite our scale, we can observe. We can measure. We can understand. We can look at ancient light and reconstruct events that happened long before our species appeared. We can infer invisible matter. We can detect energy moving across intergalactic space. And we can do all of this from a quiet planet orbiting an ordinary star in an average galaxy. There's no arrogance in that. There's no despair either. Just perspective. Understanding the universe doesn't make us smaller. It gives us context. It reminds us that being part of something vast doesn't require dominance. Participation is enough. Awareness is enough. The universe doesn't need us to be large. It only needs us to be curious. And in that sense, the story of these giants isn't about insignificance. It's about connection. About how the same physical laws that shape the largest structures also shape the smallest lives. You are made of the same material as those galaxies. And for a brief moment in cosmic time, that material has learned how to look back at itself. That's not a contradiction. It's one of the quiet miracles of the universe. And while the universe continues its vast, patient work, you don't have to carry any of that weight with you tonight. Tonight, we've met two very different kinds of giants. One grew large by accumulation, matter gathering slowly, patiently, over billions of years. Stars added to stars, gravity pulling everything inward, a galaxy becoming immense simply by never letting go. The other grew large by extension, not by holding on, but by reaching outward. Energy flowing away from its center, guided by magnetic fields, stretching quietly across intergalactic space. Two paths, two definitions of big, and yet both remind us of the same truth. The universe does not require our attention to continue. These giants keep moving whether we watch them or not. Galaxies drift, energy travels, light continues its long journey across space, all without urgency, without effort. Nothing is waiting for instructions. Right now, IC 1101 is still holding its ancient stars in slow orbits. Alcyoneus is still carrying the faint imprint of energy released long ago. Dark matter continues to bind structures together. Dark energy continues to stretch the space between them. All of it unfolds on timescales far beyond a single night. And that means something important for you. You don't need to solve anything. You don't need to keep up. You don't need to hold the universe in your thoughts. It's already doing exactly what it has always done. As galaxies drift farther apart, the sky remains calm. As light travels millions of years, this moment remains still. As the universe expands, your world can become smaller, quiet enough to rest in. This is the balance. The universe is vast, complex, and constantly changing. But this moment is simple. You are here. You are safe. And nothing is being asked of you right now. Let the giants continue their slow work in the distance. Let the stars burn quietly where they are. Let the light keep moving. You don't have to follow it. While the universe keeps moving, you get to rest. The giants are still out there. And tonight, you are safe.